Alright, today we are going to be looking at the fundamental characteristics of a sound wave. For those who didn't watch my video on what is a vibrating source, I will go over briefly what that is right now. Sound is produced when an object known as the source vibrates and causes the air around it to move. Imagine a simple vibrating source like a pulsating sphere. As this sphere pulsates, it alternately creates regions of high pressure, compressions, and regions of low pressure, rarefactions in the surrounding air. These compressions and rarefactions travel away from the source. Since the air particles move in the same direction as the direction of wave travel, sound waves are classified as longitudinal waves. This contrasts with transverse waves like those on a vibrating string, where motion is at right angles to the direction of wave travel. The first characteristic we examine is frequency. Frequency is simply the rate at which the source object oscillates. This rate is typically measured in hertz, or cycles per seconds. 1000 hertz is 1 kilohertz. Frequency is the inverse of the time period between the wave's peaks or troughs. Therefore, the shorter the time between oscillations of the source, the higher resultant frequency. For reference, the human ear is generally capable of perceiving sounds with frequencies between approximately 20 Hz and 20 kHz. This is known as the audio frequency range or audio spectrum. Next is the amplitude. Amplitude refers to the amount of compression and rarefaction of the air that results from the source's motion. The greater the compression slash rarefaction, the higher the amplitude. Amplitude is directly related to the perceived loudness of the sound. When we plot amplitude against time, we see the waveform of the sound. Compressions correspond to the positive range of the amplitude's axis, and rarefactions correspond to the negative range. The simplest form of vibration, known as simple harmonic motion like a pendulum, produces a very pure single frequency sound wave called a sine wave, or sinusoidal waveform. Most real sounds, however, are made up of combinations of vibration patterns resulting in a more complex waveform. The physical distance traveled by one full cycle of the sound wave is its wavelength, often represented by the Greek letter lambda. Wavelength is dependent on the speed at which the sound wave travels. The speed of sound, represented by c, in air is approximately 340 meters per second. Wavelength, frequency, f, and speed, c, are linked by the equation c equals f lambda. This means if the frequency increases, the wavelength must decrease, provided the speed remains constant. To grasp the scale, consider extremes of the audio spectrum. For a low frequency of 20 Hz, the wavelength in air is very long, about 17 meters. However, for a high frequency of 20 kHz, the wavelength is quite short, only about 1.7 meters. This is a important variation when considering how sound behaves when it encounters objects.